All right, it's 7 o'clock. We will get started today. So, there has been a lot of problems with
Excuse me, sir.
assignment
Still not
5.
audible, sir.
Uh, Hello, Nirut, am I not audible?
Sir, now you're audible.
Okay, 1 second, give me a minute. I will change the settings. How about now? Am I audible now?
Yes, sir, now you're audible, sir.
Okay, okay. So, is there any disturbance right now? No, right?
No, sir.
Okay, okay. So, um, yeah, so there has been, I was telling that there has been lot of issues with assignment 5, question 22, 24, and 25, I guess. So I had a talk with the professor, and he gave me few explanations. I will share it with you. So it looks like all three questions are right, and whatever we thought is also right. There is some tricks they have followed while making the question, so that's why it got little tricky when we looked at it. So let me just quickly go through that questions. Okay, so first is question 22, I believe, and think it is it's about this thrust, right? So let me explain it to you. So the thrust will be maximum for what cases have a optimally expand, or when we have optimally expanded the nozzle, we are going to have maximum thrust, right? So the question actually says the thrust would be maximum uh, in the facility when it has been expanded to optimum expansion through the nozzle, which is 0.02 megapascal. So maybe let me just quickly show that question also. Yeah, this is week 5. Yeah, assignment 5. So yeah, so this is question 2, right? Question 22. If you look at it, um, the thrust developed in the test facility be greater, lesser, or equal to. So actually, even I tried to attempt it, and it looks like I also got question wrong. Anyway, so the thrust developed in the test facility be actually greater for optimal nozzle expansion in the facility, which is so optimal nozzle expansion. When we do optimal nozzle expansion in the facility, which is up to 0.02 megapascal, it would be greater than if we had a over expanded nozzle. That is what the question is about. That is the intention of making the question. It's about the adaptive nozzle. If you adapt the nozzle such that your exit pressure is equal to 0.02 megapascal, you are going to get greater thrust. So that is why greater is the correct answer for this question.
But there is this issue that this is designed for optimum expansion for an ambient pressure of 0.01 megapascal. It is already designed, right?
Yeah.
And
So yeah,
in
yeah.
this particular question, would the thrust developed in the test facility be? There is no mention of whether it is optimal or anything else. So
Right.
we will be,
It
yeah.
has, yeah, you are right. It could have been stated better. If you look at it, there is one more line, right? So here, the thrust developed in the this thing, the thrust developed for optimal nozzle expansion in the facility. That is 0.02 megapascal. So there is a, I agree, there is a confusion in the question, but the motive of this question is like this. So you should look at it. So basically, whatever you are telling is right. If it is, let's say, if you have adaptive nozzle such that it adapts for 0.02 megapascal, that's what the second line tells, right? Develop for optimal nozzle expansion in the facility of 0.02 megapascal, then your thrust is going to be maximum. So that
Uh,
is
we are comparing two things right here. We are comparing two things. One is the thrust that is already developed by the rocket nozzle in the test facility
correct.
with, with this particular expansion of 0. 0.01 megapascal, right? We are comparing
Correct.
that thrust to
With
the thrust which would have been produced if the nozzle were designed for 0.02 megapascal.
correct.
So we are comparing these two things.
Right.
So why are we saying that this particular thrust is for the optimal condition?
Yeah. So there are two things. One is, let me write it down. So first one is nozzle design pressure is 0.01 megapascal, right? And the
Right.
nozzle design pressure is 0.02 megapascal.
Ambient pressure.
This is exit. I'm talking about exit. This is what you will design for, right?
Okay. The first one is,
So ambient is 0.02 megapascal. Okay. This is not
okay.
changing. This is not changing.
Yeah.
Okay. And the first one is you have designed the nozzle for 0.01 megapascal and you are designing the another nozzle for 0.02 megapascal. And if you
Right.
compare the thrust for these two, this is
Yeah.
going to be greater.
So could you explain it using the equation of thrust?
Yeah. So m dot into Vj plus Pe minus Pa times Ae, right? This is the thrust, right?
Yeah.
Yes,
Yeah.
sir.
Yeah. So let's say I have, let's say this is first, let's say this is second. Okay. And let me write it for first one. So this thrust is going to be m dot into Vj plus 0.01 minus 0.02 times Ae. Okay. And the second one is m dot into Vj plus 0.02 minus 0.02 times Ae, right? In these two, this is going to be greater, right? Because this has optimally expanded and this has over expanded. Over expanded thrust is going to be less. Does that make sense?
Yes.
Yes, sir.
Yeah. The so that's how the greater is the correct answer for our optimally expanded. I agree the wording should be little bit corrected, but I don't know whether it can be changed or not. So it's up to professor. Maybe I don't know. It's you have to ask professor if you have any problems with that. But this is what
But
it's actually meant. It's meant
okay,
that
we at the end we are comparing the overexpanded thrust with the optimally expanded thrust,
correct.
right?
Yeah.
So would the thrust developed in the test facility be less than, greater than, or equal to the thrust produced for the optimal case? So we are comparing the overexpanded thrust to the optimally expanded thrust.
Correct.
So
Be
overexpanded thrust
greater
should be
the
less
thrust.
than,
Correct. Over expanded thrust should be less than optimally expanded.
yeah, the entire thing doesn't make sense. That is why that is why I
Yeah, the wording
made that
is,
comment. Yeah.
yeah, the wording is not quite explicit. If you ask also, it is like question. It doesn't fill in the question actually. So it's not a statement where you are filling it. It's like would the trust be developed? So it's kind of question. So yeah, you are right. The wording should be corrected, but I think if you need mark for that, I maybe you may need to make a request for that. One thing, okay. So, but underlying concept is you should be clear. Only for optimally expansion, you are going to have uh, greater thrust. Okay,
What would be the comparison with the under expanded case?
right.
Can you just add that one,
Yeah,
please?
yeah. So let's say if you have a under expanded nozzle, what happens is this is going to be positive, right? Let's say you are expanding till 0.03 megapascal. Okay, this pressure
Okay.
thrust will be positive, but you have to note one more thing. This VJs doesn't remain same for all the things,
Yeah.
right? So for an under expanded, what happens? This Vj will also change. Yeah, in fact, for over expanded and optimally expanded, also Vjs will change. In fact, over expanded is going to be very trickier because there's going to be shock and which reduces the overall thrust by a very large amount, because after shock you are going to have subsonic, right? Or maybe less velocity. So in that way, if it is an under expanded nozzle, you are going to have, again you are going to have less thrust because of velocity you won't uh, let's say for the same area ratio, okay, no, let's say for the same uh, exit pressure, if you see in terms of efficiency how much you converted the chemical energy to the velocity or kinetic energy, the under expanded you didn't expand it to the ambient pressure, right? So
Means P by PC is not sufficiently low enough
correct, yeah, p
in this under
ha
expanded
ha
case,
ha p by
and that is
p.
why the VJ is
Yeah,
low enough. Yeah.
yeah. So, so if you just look at this equation, you might be thinking that for under expanded it would be greater thrust, but that is not the case because VJs also get affected. And what you have to do is there is important thing called thrust coefficient, which we derived, right? Which is a function of, if you remember, basically it's PE minus PA by PC, right? And plus additional terms will be there. So if you, let's say, uh, so this is not been covered, okay? So if you are interested, you can look at it. If you, let's say, optimize this thrust coefficient, if you let's say plot it for different varying pressures, and you will say only when there is optimal expansion you will have higher pressure. Even if it is under expanded, you are going to lose some pressure because you didn't effectively convert all the chemical energy. So that is something which has been not derived in the class, and you can go ahead and derive. So I think
So in this course, the CF has been defined as some sort of transfer function, right?
C star is transfer function.
What is
CF,
CF?
so CF is, how do you say CF? Um, it's thrust is nothing but, sorry, CF is m dot by PCAT, if I remember correctly, right? So it's like how you can put it. Yeah,
Yes, sir. It is the function of gamma and then epsilon, the area ratio. And the exit pressure and chamber pressure and the creep pressures.
right, right. You are right. So it is actually a, you can say it's a transfer function. That is
It's a
also,
transfer function between the force and the PCAT quantity.
yeah. You can say
Actually,
that.
it should not be m dot, but rather f by PCAT. You have written it for C star actually. CF is f by
Okay,
PCAT. Yeah,
okay. So C star is m dot by PCAT, right? Or
yeah,
PCAT by m dot.
yeah.
Yeah.
PCAT by
So,
m dot. Yeah,
yeah, yeah. So PCAT by m dot. So yeah. So it's like.
both are
It's
like
a
transfer
it's a
function.
multiple. In fact, it is not transfer function. It's like multiple. Uh, uh, the coefficient you are getting upon adding a divergence part in the nozzle. That's what it means.
And CF will always be less than one or what?
CF will always be greater than 1. So that is the reason we
Oh,
add a
okay.
divergent part, right? So if you expand it till the throat, you are going to get some velocity and you are going to get some thrust. Upon adding a divergent part, how much thrust increment you are getting is what this CF is going to tell, right?
Okay, okay.
Are you understanding how it comes? Like, so
So we are getting a thrust from the throat section as equal to PCAT, and then we are multiplying it by the divergence section by the factor CF to get the final thrust, that is F. Okay,
right,
okay,
right. So PC is the chamber pressure and AT is the throat area, right? So when you expand it till the throat, you are going to reach sonic velocity. And upon adding a divergence section, how much uh, increment in thrust or how much multiplication of thrust you are getting is what this CF tells. It's a characteristic of nozzle. So that is what it means.
Okay, so you are saying that we are not going to deal with the CF as a function of this pressure quantities, right?
CF would be function of pressure, right? So it depends on
No,
whether
no.
the nozzle is.
In this course we are not dealing with that. But in reality, that is also a function of P by
Correct.
P minus PA by PC. Okay.
Correct, correct. So if you look at the equation also, if you remember, I think it will be in the square root of some big equation which has PE minus, I think it might be outside also, plus P minus PA by PC times area ratio as Chitanda told. So there will be area ratio AE
Okay.
by AT, right? And then there will be some more parameters. So in fact, CF is a function of whether the nozzle is overexpanded, underexpanded, or optimally expanded. True. But, so when you differentiate this function in terms of pressure, you will end up getting optimal. You will end up getting maxima only at only when PE equal to PA. So that is the reason uh, the only optimally expanded is going to give you higher thrust. So you can do this exercise for yourself. Is this clear?
Yeah. So finally, if we compare the underexpanded with the so in conclusion, overexpanded as well as underexpanded will produce less thrust compared to the optimal expanded case.
Yeah.
But if we want to compare overexpanded and underexpanded while ignoring the flow separation, what will be the comparison between the thrust?
So yeah, the underexpanded would be more thrust because if you look at it in the overexpanded part, you are going to have flow separations, and uh, it is actually not good for your rocket, right? So under expanded,
Okay.
your rocket will always be operating only at the under expanded. So if you see from thrust basis, I believe if you ignore flow separation, I believe under expanded is going to be more. But it also depends on various parameters like VJ also, M dot also. Uh, but you can safely say under expanded is going to give more thrust than over expanded.
Okay, so in reality, the rockets are mainly designed for under expanded case at the sea level.
So it may not be. Uh, Sometimes they might be designed for somewhere, uh, but it is safer to design at ambient condition if you define the this thing. But it depends on which stage you are in. So if you are in lower stage, you might design your nozzle for ambient condition. If you are in higher stage, at the point of separation, what is the optimal expansion or the let's say at some point of time only you are going to get higher mass flow rate. At that mass flow rate, if you try to make your nozzle also expand optimally, you are going to get higher thrust, right? So the second stages may not be designed for ambient. It doesn't make sense to have to design the second phase um, for ambient pressure, right? So in second stage you are going to it's going to get at certain altitude. So maybe you can design your nozzle for that altitude. So it depends on the mission parameters and how your thrust profile should look like. So you cannot have a constant thrust profile because none of this rocket is going to give constant thrust profile unless it is liquid propellant. In solid propellant, it's going to have a increase and decrease. All those things is going to happen, and pressure is also keep on changing obviously. So it depends on what is your thrust profile for which mission you are trying to acquire, right? And depends on that you need to design the nozzle. So yeah, mm, it may not be necessarily you need to design for ambient. It's actually better if you design your nozzle such a way it is only in optimal expansion and under expansion, because optimal expansion you can achieve at only at one altitude, and even if it is slightly above or below it's going to be create problem. And in fact optimal expansion you will never achieve in uh, real situations, right? There's always going to be, it's not possible only, it's very difficult to achieve.
So
optimal speed.
does this mean that if the booster stages, in case of booster stages, the divergence section is going to be shorter, and in case of vacuum engines, which are at the second or third stage, the divergent part will be longer? Can we make that conclusion? Because at the end, the PE has to go much lower in case of higher stages.
Uh, yeah, so you are comparing two different things. So if you say I want to have under expansion and at ambient conditions, so there is ambient is different, right? So at higher stages, the ambient is different. So let me think. Yeah, you could make that conclusion because the ambient is going to be very low, so you may need to expand it for a very long time or very long distance, right? So if you look in terms of area ratio at higher altitudes, let's say for second stage and third stage is going to be higher, uh,
Okay. Okay.
and yeah, you are right. Yeah.
And is there anything that also determines the convergent sections length?
Yeah, it is basically, if you look at it from whatever analysis we do, it doesn't really affect what is the convergence sections, like what is the length of the convergence sections. It doesn't really affect the nozzle performance because we never take into account of convergence area ratio, right? Uh,
Also, we are assuming that at the throat the conditions will always be sonic.
Assumption, it will be sonic.
Okay.
It's
So
not an assumption.
no matter what the upstream pressure, PC and temperature are.
Yeah, it is going to be sonic at the uh, if it is choked flow. Like, so for a choke, you understand choked flow, right? So if your nozzle is
Yeah,
choked,
the mass
your
flow rate cannot increase further than that.
mass flow rate cannot increase further, and uh, only at the choked flow you are going to have uh, sonic velocity. Until then, it's going to be less. So if you assume it is an assumption. If you assume choked flow, then always you are going to have Mach number one at the throat. It's not. It's never going to change.
Yeah, but I'm asking this question that in reality,
Hmm.
means is there any condition on PC and TC which will ensure that there is choke flow at the throat? Means we should have some sort of minimum PC and TC which will ensure that the velocity at the throat becomes uh, choked.
Right, right. So you should think in this way. If you want a choke flow, so that is your main objective. You want a choke flow. Okay. For that, if you think velocity gets adjusted, your temperature gets adjusted such that it is a sonic. Okay. So your rocket motor is going to be,
Excuse me, sir.
yeah,
Sir, for a choke flow, we need to have the chamber pressure and the exit pressure same.
right. No, we no need to have same pressures. So chamber pressure will be something. There will be exit pressure. Okay. There will be, to have a choke flow. If you plot that graph, if you, so that is where actually I'm coming. This is m dot. This is PC by PE, right? So in order to have choke flow, it's going to be like this. This is how it varies. Okay. So if you have, this is it PC by PE as,
Actually, P by PC.
right, right, sorry, by PC. So as and when this pressure decreases, so to quickly answer your question, it depends on chamber pressure and the exit pressure, the ratio. Okay, so for that, it depends on ratio. For that ratio, you are going to have a certain mass flow rate, a choked mass flow rate. Okay, and so what was your question? I lost track of your question.
Yeah, my question was that what would determine the PC and TC to ensure that the throat is always choked or choked during most of the flight?
Right. See, for a given pressure ratio, you are going to have choke flow. Okay. Um You need to make sure that it is not, let's say if you think about it as a, let's say initially PE is equal to PC. There is no um, explicit,
Pressure gradient.
yeah, so it is not, it is a pressure ratio, it is not a pressure value. That's what I'm trying to say. So
Okay,
for a
so
given pressure
in this,
ratio,
yeah, in this particular graph, if we reduce the back pressure, which is the PE,
hmm,
then we are moving towards the left
right,
in the x-axis, and
right,
so we are moving close towards the choked condition, right?
correct.
So there are multiple values of PE by PC for which the flow will be choked.
So yeah, yeah, true. So above this PE by PC, so PE by PC, some less than some certain value, let's say some PR choke, you are going to have choke flow. So your pressure ratio should be less than this critical pressure ratio for which your nozzle is choked. So it
So
is
we
not
can,
the exact value of pressure. That's what I'm trying to say. It's not 5 bar pressure or 10 bar pressure. It depends on 10 bar and 1 bar, or let's say 10 bar and 5 bar. If you compare 10 bar, 5 bar, and 10 bar,
okay,
1 bar.
it would depend on the optimal condition for which we are designing. So let's say we are designing for 10 kilometer altitude. So PE will be equal to PA at 10 kilometer. So PE is fixed based on that, and thereafter we determine the PC based on this particular choked condition.
Right. So there is a possibility you no need to you no need to have
Is
optimal
this correct?
expansion for choked flow. You can even have over expanded nozzle. You can even have under, still it is a choke flow. You know why?
Okay.
Because
Okay.
at the throat you are going to reach Mach, and then you are going, so Mach 1 is choke flow. After that you are becoming supersonic, and then because you cannot reach the pressure differences at the exit, you have a shock or expansion waves. So there is a critical pressure ratio that doesn't depend on optimal expansion. It depends on the area or the profile of the nozzle. Let's say you have an area ratio. So this PE by PC depends on area ratio, right?
Yeah. Yeah.
Yeah. So if you have a area ratio of, let's say, 3, for that we have a critical pressure ratio for which the mass flow rate is maximum, right?
Now,
Or
in that case, we are doing the analysis thing, right? We already have been given the. I'm thinking in terms of design, like going
yeah,
back from the optimal condition to the PC to the AE. So AE will be given based on this, I
right.
guess.
So if you think backwards in terms of design, let's say you want to design a nozzle from which you need to take off from the ground, let's say 10 kilometer altitude. Okay.
Yeah, yeah,
Now, if you want to design that nozzle, you know how much thrust. So that much the thrust has to be made. Let's say you design it for ambient pressure. Okay. So when you design it for ambient pressure, you need to and let's say you fix a area ratio. Okay. Or let's say you pick you know the rocket, your rocket's combustion chamber pressure, and you are, let's say you are modeling for a optimal expansion. So for that, pressure ratio. Using the pressure ratio, you get the area ratio for the nozzle. You understand? It depends on what is the chamber pressure and what is the exit pressure.
okay, okay,
Okay. So if there is a possibility that uh, it cannot be choked flow, but that happens um, when you do not design it properly. Let's say you are designing from 1 atmosphere to 10 atmosphere, 1 atmosphere to, let's say, zero point 0.5 atmosphere. Let's say at 10 kilometer altitude, it's zero point 0.5 atmosphere, and your 1 atmosphere and zero point 0.5 atmosphere uh, should be in the range such that pressure ratio is always greater than this critical pressure ratio. Okay, are you getting my point?
yeah, yeah, yeah,
So PE varies. Okay, PE can vary, and there is chamber pressure which cannot vary. It depends on, once you select a propellant, it won't vary, right? So this uh, so you are going to have PE by PC, right? So PE1 by PC, PE2 by PC, PE3 by PC. You need to make sure that all these PEs are actually uh, less than this critical pressure ratio of choke.
okay, okay,
Then you are going to have always choke flow, and you are maximize the mass flow rate, right? If you didn't maximize the mass flow rate, anyway the pressure is going to rise inside the combustion chamber, and you are going to anyway adjust it. Pressure ratio will rise. So yeah, this is how you can design. This is one way of designing. Um, yeah. So does it make sense?
Yes, yes. So the goal is to optimize the thing for the entire trajectory, I
Correct.
guess.
So the goal is to optimize the mass flow rate. Number one, first goal is to optimize the mass flow rate. That's why you always want the choke flow. And second is to optimize thrust. So you will either be in under, and the third is you're concerned with safety, right? So you won't go for over expanded.
Yeah.
That
So
are those.
in case the flow is not choked, the thrust will also be, I think, non-existent,
It
zero.
will be totally affected. So it won't be
Okay.
non-existent. The velocity would be very less. If it is not a choke flow, your velocity is going to rise like this. This is the center line, right?
Rise and then decrease.
So it's going to rise like this, and then it's going to decrease. You do not want low velocity. You want this high velocity, right?
Okay. Okay.
This is not choked. That's why you go for choke flow. You need to increase it as much as possible.
Okay. Okay.
All right. So the second question was the flow separation, right? So
Right.
it was like we discussed only. Yeah, so basically, if you compare two flow separation process, let's say in a conical, so what was the question? Let me open it again. So the flow separation in conical convergent divergent nozzle takes place in the nozzle exit pressure much lower than the ambient pressure, which means like if it, let's say there are two cases if you consider. Um, so PE less than PC. Okay. Um, Sorry, not PC. It's a PA, right? Similarly, there is
Right.
one more which is much less than PA. I'm exaggerating, much less. It's not much less. Let's say PE is, let's say, 0.5 times PA. Okay. And here PE is, let's say, zero point 0.2 times PA. In that case,
As per the Sommerfeld criteria, sort of 0.3.
yeah,
Yeah.
Sommerfeld is there. Yeah, yeah, that is true. But so flow separation of conical
So
conversion
summer
takes.
field is for 0.4, I guess.
Yeah, yeah, but I'm just giving you for a comparison. Okay, Sommerfeld is for 0.4. Yeah. So for this question, why inertial forces accelerating to the flow is actually delaying the process. That is that is what it's been asked. The flow separation of conical convergent divergent takes place for nozzle exit pressure much lower than ambient pressure due to inertial forces accelerating the nozzle. So let's say if you compare these two conditions, okay, which is prone to which is easily prone to flow separation,
The lower one.
right? So the I mean we are talking about, so because of inertial forces accelerating the flows, yeah. So the if you have lower okay, so okay, let's not use this. Let's say a flow separation happens, okay, for one case where as you said there is a Sommerfeld criteria. PE is uh, zero point 0.4 times PA, right? That is what the uh, Sommerfeld criteria tells, right? So is this for conical nozzle or contour nozzle?
It is for conical, I guess. Yeah, conical node.
So this is for conical nozzle. Now, uh, the if it is, if you, let's say the flow separation happens, let's say at zero point 0.2 times PA. Okay. Let's say if you consider PE is much less than PA, let's say flow separation happens at zero point 0.2 times PA. Then what it means? There is another nozzle which says the flow separation happens for a much below ambient pressure, right? Flow separation happens for much below pressures than ambient. Then what it means, the inertia forces has actually dominated the flow, right? Dominated the adverse pressure gradient. So yeah, so flow separation of conical convergent divergent nozzle takes place for nozzle exit pressure much lower than ambient pressure. So initially there is one ambient pressure which is P less than PA, and for that flow separation happens at some point of time. If you reduce it even more and later it happens flow separation, which means inertia forces are actually contributing to uh, delay this flow separation. So it is supposed to be comparing two nozzles. Okay, one when the flow separation happens at higher pressure, one when happens at lower pressure. So
So
what
inertial forces delay the flow separation, right?
inertia forces delays the flow separation. It has
But
to
here it is asked that the flow separation is due to inertial forces. That is what the answer has been given.
yeah, it is the due to is because of lower pressures. So from here to here, it is it's not for pressures lower than ambient pressure. It's pressures much lower than ambient pressure, right? So there you need to compare with two conditions here. Okay, one is pressure is lower than ambient pressure. Here, let's say you can identify this as PE less than PA, and you identify this as PE less than PA, which means much lower. Okay, so when your pressure is much lower, and at that point if the flow separation happening compared to P less than PA, it is due to the much lower condition has more inertial forces which dominated the adverse pressure gradient. So that is what you should take from this question. The conical takes place for a nozzle exit pressure much lower. So again, this is also not well stated, but this is what Sar meant. That's what he said about why it is correct.
Actually, sir has given an explanation in which he has also mentioned about this
Boundary
boundary
layer.
layer not having adequate velocity.
So that is
So
true.
this is totally contrary to the answer that has been selected.
Boundary layer not having adequate velocity is always present, right? So when a boundary layer does not have adequate velocity, is what is going to lead to flow separation. But the flow separation process can be delayed when we have higher inertial forces. That is what you need to understand. So in the boundary layer, you are always going to have low velocity. Okay, whether it is high pressure or low pressure, and if your inertial forces cannot overcome it, then only you need to uh, then only flow separation happens, right? So if at some other nozzle for which the separation happens at much lower pressure, the reason is not due to boundary layer velocity, it is due to inertia forces. You have more inertia forces, right? Let's say if you compare conical and convergent divergent nozzle, in conical nozzle it the flow separation happens here, but in a contour nozzle, right? Sorry, contour nozzle you are going to have high divergence, right, initially, which means it has already accelerated to a very high velocity here. Okay, when you have very high velocity here, you are going to have less chances of, let's say this is the place, let's say PE is zero point 0.4 times PA, right? Similarly here PE is equal to zero point 0.4 times PA, right? But there is a less chances that the flow will separate here. The flow might separate here, somewhere here, right? So it has gone below. The reason is due to you accelerated the flow to a very high velocity. This is due to inertial forces. Is what uh, it's what it actually delays the flow separation. That is what the intention for this question. Does that make sense? It is, you need to note this word much below, right? So even when PE is less than PA, you are going to have low velocity boundary layer velocity, and if PE is much below also, you are going to have boundary layer velocity. But when it happens at low velocity, it means inertia forces has dominated the pressure gradient, or you are going to have higher wall boundary velocity at the places where the inertial forces are dominated, and when the you have less chances of flow separation. Is that making sense?
So if the exit pressure is much lower than ambient pressure, flow separation is more likely, or if it is not that low.
So exit pressure is lower than P ambient, so it, it doesn't matter. So when there is a over expanded nozzle, you are going to have flow separation, right? And based on Sommerfeld criteria or the other criteria, you are going to, there is one uh, uh, pressure where you are going to have flow separation, right? Whether it is, it doesn't depend on exit uh, pressure, like I mean, it doesn't depend on exact pressure values, it depends on PE by PA, right? So if you are going to have for a given ambient pressure, at the point where your ambient exit pressure is zero point 0.4 times PA, you are going to have I think it's PA is equal to zero point 0.4 times PA, is it? I'm not exactly sure about the PN is equal to zero point 0.4 times PA. So it's a local pressure, right? So when you have lower exit pressure, if your flow is accelerated, then you are going to have less chances of flow separation, or you will delay the process of flow separation to a lower pressure. That is what it means. Let's say if you take a just conical nozzle, and if you want to let's say you have a high ambient pressure, okay, and you are slowly reducing the ambient pressure, the flow separation would have happened before itself. So for example, for this is the conical nozzle, let's say when you have ambient pressure to be very high, okay, let's say 1 bar, okay, the flow separation might happen here. When you reduce it to zero point 0.5 bar, separation will happen here.
So let's say the ambient pressure is fixed at 1 bar, and we are comparing the conical nozzle with the contour nozzle. Both are overexpanded at the same pressure. Let's say PE of the conical is exactly same as the PE of the contour.
Okay,
So which one will be more likely to undergo flow separation, and why?
conical, because here the expansion is going to be uniform, okay. So uh, uh, okay, here also ambient pressure is 1 bar, here also ambient pressure is 1 bar, but as per Sommerfeld criteria, or let's say if you just, if you forget what Sommerfeld criteria is, uh, if you just plot the pressure, okay, so this is along length, let's say this is along x, and then this is pressure P exit, no, let's P exit. So how do you write pressure? Okay, so here it is throat, right? So your pressure is going to drop till throat, and then you will continue to drop, and then you will see that there is a high pressure, so you will raise again, and then you will go and reach this ambient pressure. See, this is the ambient pressure.
So this one is for overexpanded.
This is for overexpander. So this is a normal shock. In reality, it won't happen, but just for understanding, you can understand it like that. Okay. In reality, there will be oblique shocks and flow separation happens. This is for not a
Okay.
flow separation case. So this is like at this point itself you are going to have flow separation. Okay, and the pressure will rise, but it won't rise like this, and there won't be any normal shock. You will have oblique shocks, and you see the inward motion of the gases will be happening inside the nozzle itself. Okay, so all these things will happen, but for understanding you can think it like this. Let's say you reduce the ambient pressure, and it will go something like this and then reaches here. So this normal shock gets transferred till it ends here. So at this point it's going to be optimal expansion. Let's say if you keep the ambient pressure constant, let's say this is my ambient pressure, okay, and what you are planning to change.
The type of the nozzle.
Okay, so if you change the type of the nozzle from conical to uh,
Contour.
yeah, contour, right? So at this point of time, let's say this is conical, okay. For contour, it again is going to remain same till, or it doesn't matter whether it about the convergence, okay. You can just ignore the convergence. If you just look at the divergence, the pressure gradient is going to be large down, right? So at this point, it's going to be go down, and then there's going to be flow separation happens, and it will reach the PA. The reason, if you look at these two, so this is for X conical flow separation, and this is X contour flow separation. Okay, so the reason it gets downstream is due to inertia forces which already accelerated. If you look at it, you are having high pressure gradient, right? So you suddenly expanded to a very high velocity within a small distance of time, and because of that there's going to be high velocity inside the boundary layer. It's going to be it's going to be high velocity inside the nozzle, and you're going to the inertia forces is going to overcome this sudden rise in pressure gradient efficiently. So that is the reason you get delayed, but still there will be flow separation. At this point, it may not be able to overcome. That's the reason flow separation happens. But at this point, it has enough inertial forces to overcome the pressure gradient. So here the pressure gradient is like this, which means let's say PA by PCF. Okay, and this cannot be overcome by conical, but it can be overcome by contour. Okay, because of high velocity we have. That is the reason.
So from this graph, we can conclude that the contour nozzle can reach much lower PE before flow separation happens
Right.
compared to that of conical nozzle.
Right. And the reason is it has high inertia forces. That's all.
Okay, but that sounds like again contrary to the question that conical nozzle can reach much lower than the ambient pressure.
So you
This is a
compare two
little
conical
confusing.
nozzle. You compare two conical
Oh,
nozzle. One is this one, and one is this one. Right. This is due to we have I. So the what question says is, go back. So it has one word like much lower than ambient pressure, right? So the flow separation in a conical nozzle takes place for a nozzle exit pressure much lower than the ambient pressure. Due to what? So it takes place at lower pressure, lower nozzle pressure than ambient pressure, but some other nozzle is going to take place at much lower pressure, which means it has high inertia forces which delayed the pressure to a much lower pressure. That is meant. If you it's The intention is the inertia forces is going to delay the flow separation. That is the intention of this question. You
so
can
that is
think
why
about
the
it.
conical nozzle can go much lower because the inertial force is aiding in delaying the flow separation.
The contour nozzle is going to have higher. So you do not compare. So when you compare conical nozzle, right? It doesn't talk about
Yeah, yeah.
contour
Means
nozzle.
in conical
Ah,
only, the
hmm.
inertial force is allowing the flow separation to happen much later, so that we can reach much lower P.
Right, right. So there are two conical nozzle which has more expansion and which has less expansion. At the when you compare these two, the less expansion is going to uh, have the flow separation is going to happen much at a very earlier stage than the higher expansion, because higher expansions have higher inertia forces.
Yeah, but the question is really confusing, the wording.
Yeah, wording is confusing. I agree. Uh, Even professor also agreed. The wording can be better stated, uh, but I'm not sure. So the underlying concept is this. That is what I need to explain. So that is the intention. He told that this is the intention to ask this question, and
But from the graph that
hmm,
you have drawn just now, the overall conclusion is that compared between contour nozzle and conical nozzle, contour nozzle uh, can expand to a much lower pressure without going into flow separation compared to that conical nozzle, right?
correct, correct.
Okay.
Yeah, that is true. And now coming to 25. So by now you should know what is the solution for 25. So the like you we already talked about contour nozzle. Contour nozzle is having high divergence, right? Initially,
Yes. Yes.
initially it has high divergence. So the velocity is going to be it is going to expand more initially, right? And then there is going to be slower expansion in the later part of the divergence. So you might probably wondering, slower expansion in the later part of divergent is the correct answer, right?
Yeah.
Yeah. So this has to do something with the boundary layer. Okay. So here you are viewing it in the core region. So in the core region, there is going to be very high expansion initially and lower expansion in the later part of diversion, right? But in the uh, boundary layer along the walls, okay, wall boundary layer, uh, there is going to be initially if you look at the boundary layer. So let's say if you have a zoomed in view, initially the boundary layer is going to be small, and suddenly you have expanded to a very high velocity. So your u infinity is going to be very high. So you are going to the boundary layer will get adapted to this higher expansion much later. This is the reason. If you have higher velocity, you are going to have higher expansion, right? But this higher velocity is going to get achieved near, I mean, inside the boundary layer. This higher velocity is going to achieve at the later part of the divergent than in the initial part of the divergent. So, in a core region, higher expansion is at the initial part, but inside the boundary layer, okay, the dynamics is little bit different. And if I want to simply explain it, okay, the higher expansion happens at the later part inside the boundary layer, okay. So that is the reason higher expansion is correct answer. But
But in this particular question, there is no mention of boundary layer or core flow. We are
yeah, exactly. So
totally
that is
confused.
what I'm also wondering. So they didn't state that which region we are talking about.
And
So
even in the lecture, we have not discussed anything related to boundary layers,
yeah,
growth of boundary layer, or the expansion in the boundary layer. We
I
have
see.
kept the flows to be almost similar between boundary layer, and we are mainly dealing with the core flow only.
So, in fact, all these flow separation analysis, if you want to talk about in detail, you have to do 2D analysis. You cannot have 1D analysis. The 1D analysis is just says
Right.
center line velocity, or let's say the equivalent velocity or averaged velocity along a cross section, right? It doesn't, in 1D you cannot even consider the effect of viscous. When you talk about boundary layer, you need to consider the effect of viscosity, right? So we never did a no slip condition at the wall, right? Walls of nozzle. So when you talk about flow separation, or when you talk about this. boundary layer, you need to do a 2D analysis. You need to come up with a 2D analysis. Until we do 2D analysis, we won't be able to exactly say which is better, right? So in this course, it has not been uh, thought, or it has not been discussed much. So uh, but the reason for this to be correct answer, that is what he said. I'm not sure about how the grading or how it will change, or um, like how do you want to go forward with it. So
Okay,
that
okay.
only professor
So
can do the thing. But
yeah, yeah.
I'm just giving you a physical insight, like why it is the right answer.
So in the core flow, initially there will be more expansion because there is large deflection of 10
Right.
to 15 degree,
So
and thereafter it is 4 degrees, so it is less expansion.
right. So here we saw, right. So there is a high expansion here in this graph. If you look at it, even if you go back and look at the professor's lecture, he will draw the graph like the if a conical nozzle is like this, the contour nozzle is going to be like this, which means there's a higher
Yeah,
expansion
yeah.
initially in the core flow. Yeah.
Yeah, actually I made the answer based on that only, that
Yeah,
graph
yeah.
only, because that makes
Yeah, if you
sense.
look at it, I also made the answer based on that, and my answer is incorrect.
Could you please explain that boundary layer expansion once again? Like why it is more on at the beginning part and less at the
So
later part?
boundary layer. So when we do a boundary layer analysis over a flat plate, we have considered a lot of assumptions, right? We considered velocity at the far flip to be u infinity, and we used to draw a boundary layer like this, right? But here you
Right,
cannot make those assumptions. U infinity is a function of x. It's keep on varying, right? So initially there will be a boundary layer. Initially at the throat there will be some boundary layer, okay, and suddenly you have expanded it to a very high velocity, and uh, this the fluid in the boundary layer needs some time for its expansion, because uh, the wall is adjacent to the wall is zero, right? So you cannot change the wall velocity. So here the velocity is zero, here it is u infinity, and you need some amount of time or some amount of distance to get adjusted to this u infinity, right? Or in fact, if I want to like crudely draw the boundary layer, how it varies, it might be something like this, and it is still going to be a lower velocity. I mean, you won't even achieve steady state while doing so, right? So only here, what do we say? U is nothing but 0.99 times u infinity, right? So that is for um, achieving a steady state. But here also, let's say if you assume steady state, here it needs some distance to get adapted with the u infinity. So as it goes and goes, it's going to have boundary layer thickness is going to be high, and here is where you are going to have higher velocities. So uh, it's a very crude explanation. You cannot explain it very easily, and I'm also not an expert in that.
So boundary layer thickness increases means less expansion. Is that what we can conclude?
See, expansion is something to do with pressure, okay, and or if you think in terms of velocity, if the velocity increases, the pressure decreases, then only it's called expansion, right? So here, um, the inside the boundary layer, here the velocities are going to be slow, and here the velocities are going to be high, okay, and that is the reason to have we have higher expansion in the later part of the divergence
Okay,
inside the
this is
boundary.
exactly opposite to that of the core flow.
Yeah, it is, or you can say it is a delayed process in terms of core flow. Core you suddenly expanded, and but this expansion is felt later in the boundary layer. You're getting my point? See, in the core flow, you are going to have very high velocities, and this high velocity is going to keep on increase. velocities. Here it will be low velocity. Here suddenly you have high velocities in the core flow, and this velocity is going to keep on increase. It's not going to decrease as here. Here nothing is decreasing, everything is increasing, but expansion rate is more in the initial part in the core region, but expansion rate is more in the later part in the boundary layer region. That is what uh, you need to understand. It is not opposite. If you say the expansion is at
Is,
slower rate and reaches maximum at the uh,
is this phenomena explained in more detail in the books of Professor Ramamurthy or Sutton? That
so so I'm not sure if this phenomena is fully explained here. It is a uh, it's a highly advanced topic. I am not sure why it has been included in this fundamental course, but anyway, um, just to introduce you that flow separation happens is critical to the this thing, but I'm not sure
okay,
which book
okay,
you could follow. If
okay,
I come to know, I will let you know
okay.
in this, and I'm not sure how this works. Maybe you can ask the another TA. I'm not sure whether he is dealing with this kind of flows.
Nikhil, you're
Huh.
referring to
Okay.
Nikhil?
Yeah,
Okay,
yeah,
okay.
yeah. You can talk to him also about this.
So, is there a possibility that these three questions, because most of these are like out of scope, because based on the professor's lecture, I have made this solution, but this doesn't make sense again. So,
Right, 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 right.
can
So,
this be like removed
uh,
from the grading?
actually, I cannot do anything about it. But what you can do is you can ask him in the discussion forum. If he agrees, it's up to you. So I just asked him
Okay,
for the
okay,
explanation and what should I convey it to you, and he gave me the explanation, satisfactory explanation. So I'm just giving you the explanation why it
okay,
has to
okay,
be.
okay,
About the grading, I'm not sure. I may not be able to do anything for that. You can talk to professor, or you can use the discussion forum for that.
okay.
All
Thank
right.
you.
Okay. So, is there any other questions regarding the last week's assignments or previous week's assignments covered till now?
In one of the week 6 assignment, one of the question had mentioned about a specific heat ratio, but
Okay.
the answer that was chosen as correct is a specific heat instead of a specific heat ratio.
Sure. So, what was the? Did you look at the solutions?
Yeah, in the
In
solution
solution,
also it is giving a specific heat ratio, but the answer that is given is a specific heat instead of
that they
ratio.
might correct. That's not a problem. In solution, you were right, right? When you see the solutions for the. Uh,
No, no, in the solution also that ambiguity is still there. Let me check.
okay. So this the 19th one you are telling mean specific heat ratio.
Let me check it.
It's 19. Okay. In okay, it was wrote mean specific
Yeah,
heat
yeah.
ratio, and then
19 and
CP is
12.
calculated. Yeah, 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 yeah,
19 and 12, yeah.
yeah, yeah. So yeah, that is I think a problem with the question. So did you raise the issue about it?
I
Did you
think
get any?
one of the student as Sri
Okay,
Lakshmi has raised this issue. Yeah.
okay. Did they get any reply for that?
Not yet, I guess, not yet.
Okay, so yeah, that should be corrected. It's not a problem. It was clearly stated, right? May it should be corrected. I'm not.
So 19 is asking for a specific heat ratio, but the answer is a specific heat. So
Yeah,
that
yeah.
is ambiguous. But what
Okay.
about 12? Question number 12.
Well, so it is mean specific heat of combustion. It has given combustion specific heat, right? You need to calculate CP of
No, it
just
is
CP.
simply saying mean specific heat. So do we consider constant pressure or constant volume? It is not mentioned exactly like is it. If
Yeah,
it is a
so usually we deal with only CP, right? So
okay,
we should use
Excuse me,
CP.
sir.
Uh-huh.
Sir, in this 12th question only, so the answer is like 53 point from 53 to 53.7.
Mm-hmm.
So that will be in joules. For kilojoules, it should be 0.05.
Oh, okay. It's given kilojoule, no? So yeah, please make that request also. It should be corrected. The range, it it should be possible to correct it. Yeah, the solutions also gives 53 joules, right?
Yes, sir.
Yeah, then it's fine. No problem. So yeah, basically to answer Samam's question, its specific heat is nothing but CP only you should consider. Uh, because CP is where we use everywhere. So when usually people can drop out the term pressure for constant pressure.
okay. Actually, I saw this mean thing, and
Mhm.
I calculated the mean of CP and CV, and
Okay.
that came out to be wrong. Yeah.
Yeah. So see which one? 12th question, right?
Yeah, yeah, it is asking for mean specific heat. So I made the assumption that it must be a mean between CP and CV because neither pressure
Oh.
nor volume is mentioned.
Okay.
So
Okay. 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 Okay.
there I made the mistake. Yeah.
It's just mean specific heat is for the product species. It has nothing to do with CP and CV. See, we never have both CP and CV in the same equation, right? If we solve for enthalpy, we will have CP. If we solve for internal energy, we will have CV. So there's going to be nowhere you will have only uh, you are going to use CP plus CV by 2. Okay,
So mean in the sense that it is a product mix,
it
and we
makes,
are
yeah,
okay. Okay.
specific heat of combustion products, right? So combustion products specific heats mean you need to take.
Okay. Okay.
All right. Any other question? Question? All right. Um, I think I have one more question here to solve today. Um, I saw the assignment 7, I believe it's 7. It was again like to calculate the temperature and characteristic velocity of a given propellant. So I thought in the last class we rushed a little bit in the later part of the session. So I thought I will again do one more different problem, which will give you an idea how to calculate all these parameters accurately. Okay, correctly. So we have a propellant, nitromin propellant, which is HMX. It's an acronym for her majestic explosive. It's a it's a Britain explosive, but it can also be used as a fuel. Okay, a propellant. So there is a 85% of HMX added to HTPB binder, and the chemical formula is given, and the heat of formation is given. Okay, and the chemical formula for HTPB is also given. The heat of formation is given. Now you need to find mixture ratio, stoichiometric ratio, moles, heat release, temperature, and characteristic. Whatever we did last time, the same thing we are going to do again. Um, so please make yourself clear about how to calculate mixture ratio and the number of moles of each and every uh, species in the product mixture. Okay, so let's start writing it. Um, Maybe you can help me in going through the steps, everything, because it's already been uh, addressed in the previous session. So we have HMX, right? And then we have some A times C200 H302 and O2. This is HTPB. In fact, it's a polymer, so that's why it's C200 and H302. Anyway, uh, which gives, so what are the combustion products it will give?
Exactly,
CO.
sir. How do we estimate that?
Right. So you have a fuel, okay? You have a fuel and oxidizer, and you consider an ideal set of products, okay? So upon combustion, what is the product species you are going to get? You will you will be getting CO2 H2O, right? This is the major product species because it's hydrocarbon, and you are also having hydrocarbon here, and you are going to get CO2 and H2O. And
Sir,
since in
are
a
we considering at stoichiometric?
no, we didn't consider it yet, but first case, what you can say is in a stoichiometric, you are going to have ideal set of products. First, you consider ideal set of products, and you try to equation, and in addition, you consider all the species. Okay, so in fact, uh, if you do a equilibrium analysis, if you take a combustion course, we would never do this. So what we write is, let's say if you want to do this combustion and if you want to write the get the product species, this is going to give us CO2, CO, H2O, H2, O2, H, O, N2, okay, N, OH, H, what else I missed? N2O, then NO2, and then uh, what else we can add? We can keep on adding. It's like you can have n number of product species, okay? But you, how many atom balances you have? You have carbon, hydrogen, nitrogen, and oxygen. You have four atom balances, and you need to find out what are the mole fractions of all these species. Is it possible to find out?
Yeah.
How do you find out? Why don't you find out for this?
We have to solve a large number of algebraic equations.
Yeah, I agree. You have to solve large number of algebraic equation, but your system is closed. Is it determined?
Oh, no,
Equations you
no.
have? You have only four atom balance equations, right? Or you can say element balance, right? You can do carbon. Let's say, let me write it down for you. Let's say this is here we wrote A, no? Let's change this to let's say some other lambda. Okay. Now let's write this as A B C D F G H I J K L. Similarly, you will go on. Let's say let's consider till L only. Let's forget this. Okay. Now I have L unknowns. Right? All these are unknowns, and I have four equations. How much is L? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 unknowns. You have 12 unknowns and you have four equations, right? Will you be able to solve? It's underdetermined system, right? With four equations, you can solve only for four unknowns. You cannot solve more than four unknowns.
Yes, yes.
You see my point?
Yeah.
So just by looking at it, you cannot solve this equation. What we do is, in order to have a equilibrium in this mixture, right? This is a mixture, product mixture, right? After combustion, you are going to have this mixture. In order to have equilibrium in this mixture, this equilibrium mixture should follow uh, basic law, because it all should come from basic law. Whatever we did is mass conservation. This atom balance is nothing but mass conservation. If you it is it's called atom balance, but if you can rewrite it as a mass conservation equation. Similarly, from some basic fundamental law, you should be able to calculate the equilibrium of this mixture. And what is that law here we use is second law. Second law of thermodynamics. Second law of thermodynamics will tell how this mixture should be, or how the equilibrium should shift, right? So that is what second law tells. Your entropy of the universe should always be maximized. So if I have a equilibrium mixture, then if I want the entropy of universe is maximized, then what would be my mole fractions? Okay, so I'm giving a crude explanation for this, how we get this 12 unknowns. So by applying this second law, you will have additional 8 KP equations. We say it's KP equations. It's called equilibrium constants. KP, you know, right? It's an equilibrium constant. It considers whether H2O can dissociate into H2 and O2, or H2O can dissociate into OH and O. If it wants to dissociate, how much it will dissociate. It depends on temperature of a mixture. If it is a high temperature, you are going to have dissociation. If it's a low pressure, again you are going to have dissociation. If it's high pressure, less dissociation is going to happen. So this is going to depend on both pressure and temperature, and this pressure and temperature again depends on energy conservation. So you need to solve energy conservation, this 4 atom balance equation, and you need to solve some 8 kp equations. Okay, it's called it comes from Gibbs free energy. So I'm just giving you an idea how it is calculated. If you are interested, you can go take a combustion book and you can study, or you can take a combustion course to study. Okay.
So is this what the CEA also does under the hood?
Yeah, so inside this CEA, chemical equilibrium analysis software, for example, it's NASA CEA, right? There are few other like GASEC, I guess, and then Cantera. Then there are a lot of other solvers which does. What it does is it solves this highly nonlinear coupled algebraic equation in order to get each and every species composition. But this is going to be very complicated in a fundamental course for a rocket propulsion, and this is also not the aim, right? In order, we need to introduce you to the concept of combustion so that you should understand the pressure and temperature and its effect. That's why we
Yeah.
didn't go into the detail of these things. Okay. Instead, what we did is we are going to take a workaround for this. We won't consider let's say O2, HO, and then N2, NO2, N2O, OH, CO. If needed, we will consider this CO. If needed, we will consider O2. If needed, we will consider N2. Okay. We won't consider dissociation at all. So dissociation is completely neglected. But dissociation is totally is going to affect your system if you have high temperatures. Okay, but we are just taking a workaround in order to get a rough estimate. Okay, that is the reason we do this. Do you have any questions? Is this clear why we are so this is how you properly calculate mole fraction of each and every species. You have to consider all the species available. Okay, because you don't know what happens at the end of combustion. It can nature is not bound to give only CO2 and H2O. It works on its own ways, and it is governed by only few laws, like first law of thermodynamics, second law of thermodynamics, and conservation principles. So you need to come up with some idea of using these conservation principles in order to achieve, or in order to predict what will be the mole fractions. Okay, so we won't go into these complications. What we do is we just consider. Let me just draw it again. So I just want to make sure this is not the correct way of doing it, uh, but we are just doing a workaround in order to solve it, right? So because if you have 12 equations, 12 algebraic equations, and it is also going to be nonlinear, because if you take a KP equation, it's going to have exponential factor in it. So solving it with hand in class is going to be difficult, and we have to use some softwares. But let's not go into those details in this course. So that's why we avoided this in that course. So what we are going to do is we will just assume ideal set of products, and then the excess we will make it as a uh, we will consider as and when required. Okay, so what we also, you need to remember what we did in last time also. We said that oxidizer is highly reactive with hydrogen, and first H2O gets formed, right? That is an important reaction. So if that happens, so what you do is first, thumb, it's not a law or something, I'm just giving you a rule of thumb so that you can find the mole fractions. The first is oxidize all H2O. Okay, and once you oxidize everything, if you have leftover oxygen, okay, then you need to oxidize all H2 to H2O. Okay, oxidize all carbon to CO. Okay, first it forms carbon monoxide. Okay, and then if there are leftover oxygen, if there is leftover oxygen, go left, then CO to CO2. Okay, it's just so when you do this and if you calculate the mole fraction, it will be almost equivalent to what you get in CEA. Okay, so when you do a CE analysis and when you do a detailed calculation, it will be almost equal. So that's why we have a rule of thumb, which is not a law, but it's a rule of thumb which is always seen to be correct. Okay, if there are no oxygen left, okay, if there is no oxygen left, then you just leave it. If there is remaining carbon, just put carbon on the other side. If there is remaining C or O or O2, just put it in the products. Okay, so that's what we will do again here. For that, first we need to find out what is the lambda. Okay, so this lambda we need to find out. So what has been given is mixture ratio. What is mixture ratio? It's mass of oxidizer by mass of fuel, right? Of oxidizer. Here you consider HTPB to be oxidizer and nitramine to be fuel. Okay, so you need to find N of HTPB times molecular weight of HTPB by N of HMX molecular weight of HMX. Let's quickly calculate molecular weight of HTPB. How much it is coming? It's C200 H302 and then O2, I guess. Is it, yeah, O2. P200 times 12 plus 302 times 1 plus O times, sorry, 2 times, right? So is this clear what I'm doing? How I'm finding the, how I'm using mixture ratio to find the number of moles? Okay, 2734, we have answer 2734. What is it going to be? Okay, because when you substitute it elsewhere, you need to convert into kg per mole, which you need to take care. Okay, and then similarly, if you want to calculate HMX, how much is going to be? By the way, if you have doubts till now, whatever we have done, please stop me and ask. It's going to be C4H10, sorry, H8N4NO24, H8N4NO24, which is it coming? So it's going to be 4 times 12 plus 8 times 1 plus 4 times, is it 14? I guess it's 14 plus 4 times 14 plus 2 times 16, right? How much is it?
296.
90? 296. Okay. I believe this is right. Yeah, 296 is right. How do we find n of so what is the n of HMX? So here if you look at the questions, everything is for per mole of HMX, right? So let's take 1 mole of HMX. Okay, and it is also better best used to have 1 mole of HMX and do all the calculations. So we already took 1 mole of HMX, so n of HMX is going to be 1. Okay, now the mixture ratio is given. Oh, is it not? It's not given. So it is given. We need to first calculate mixture ratio also. Is given 85% is HMX, HMX, and remaining is HTPP binder. 85% of HMX HTPP has HTPP, right? What the question says, which consists of 85% HMX added to HTPP binder, right? So 85% is HMX and remaining 25% is HTPP. So how do we calculate mixture ratio?
Is it 85% of HMX plus HTPP or 85% of HMX added to HTPP?
85% of HMX added to HMX and remaining is HTPP. So we have you no need to calculate mixture ratio also, or if you want you can calculate. I just want, how do we convert this information with whatever this information we have, and how do we get n of HTPP? That is what I need. How do we calculate it? Let's say if I want to give a hint, you consider a 1 kg of propellant. Okay. In that we have 85% HMX, then 15% HTPP. Sorry, 15%.
Which one is the oxidizer here?
So HMX is fuel here and HTPP is oxidizer. You can assume it to be like that. In fact, if you calculate in terms of oxygen, um yeah, it depends on mixture ratio. Based on that, fuel oxidizer varies. It doesn't matter right now, but uh, how much of HTPP I need, how much of HMX I need for a given mixture ratio. Now you consider HTPP to be oxidizer and HMX to be fuel. So consider a 1 kg of propellant. In that layer we are telling 85%. So if it is 1 kg, then it's 850 grams is HMX and 15 grams is HTPP, right? Then you can directly get how many moles of HMX and how many moles of HTPP is there, right? You have a molecular weight, so you know how many moles of HMX and HTPP are there. And if you want to normalize it for 1 mole of HMX, you know what to do. Do anyone doubts, or do anyone have difficulty in understanding what we are trying to do here? It's just calculation you need to do forward, backward, and you need to arrive at the results.
At the last, what do we have to do? Normalize.
So we need to find, yeah, like you will find number of moles of HMX. You can also find number of moles of HTPP, right? So in a mixture, you know how many moles of HMX and how many moles of HTPP is there. Okay, let's say X moles of HMX reacts with Y moles of HTPP. And if I say I want to take 1 mole of HMX, then what you have to do to the Y moles of HTPP? You need to divide by X, right?
Right, right.
So you will calculate the number of moles you need, or that's how you can calculate N of HTPP. Is this clear? Maybe I will start writing. How many moles of HMX we have here? It's called it N dash. It is not normalized. Okay. And then how many moles of HTPP we have here? Number of moles corresponds to 1 kg of propellant. You need to remember that. Okay. How many moles you have? We have 850 percentage, which means 850 grams of HMX we have, right? Times what is the grams, and you need to find molecular weight, right? Then you will divide by molecular weight of HMX. Then you will find how much HMX you have. Similarly for HTPP, you know it's going to be 150 gram. You need to divide it by molecular weight of HTPP. Then you will find how many number of moles of HTPP is there. So let's say if we do this, what happens? 850 by, okay, this is not here, 6 x. So HMX we calculated it to be 296. So 850 divided by 296, it's 2.8716, right? So this much amount of HMX I have. Now in HTPP, 150 divided by 2734, how much I have? 0.0548. This much amount of HMX HTPP I have. So 2.87 moles of HMX reacts with 0.05 moles of HTPP. That is what this 85% and 15% is corresponding to, right? Then let's say if I want, let's write it, 2.87 moles of HMX plus reacts with reacts with 0.08548 moles of HTP, right? Then I want to have 1 mole of HMX. Then if I have 1 mole of HMX, 1 mole of HMX reacts with 0.0548 divided by 2.87 moles of HTPB, right? So we know that N of HMX to be 1, we consider it to be N of HMX, for which we are going to do all the calculations. And now we have N of HTPB, which is nothing but 0.0548 divided by 2.87. This is how you calculate moles of HTPB. Is this clear? It comes from mixture rule, right? So what you know is, you know how many grams are the mass ratio of a oxidizer and fuel. Based on that, you need to calculate the N moles. Which it is coming out to be. I'm getting 0.019. Is confirmed.
Yeah, it's correct.
Is this clear how we arrive at this result? Is there any other way you could arrive at this result? Uh, how about if you write mass ratio to be, this is mass of oxidizer by mass of fuel, right? So
Can we just simply divide the
85 and
15%
15.
divided by 85%? It is giving the same result.
Yeah, yeah, that is also true. You can try like mass ratios, nothing but 0.85 to 0.15. Right? Is that what you're telling?
Yeah, exactly.
Yeah. So this is a mass ratio. In fact, mass ratio for this reaction.
So I
But
didn't get that why 0.85 upon 0.15.
see, what is mass ratio?
So it is the amount of oxidizer to the amount.
It should be reciprocal of that actually. 0.15 divided by 0.85.
Here. So in order to answer your question, it's mass of oxidizer divided by mass of fuel. Right? What we know, mass of a propellant is nothing but mass of oxidizer plus mass of fuel.
Yes, sir.
So I am telling it's 85% of the propellant is uh, oxidizer, which means 0. Sorry, 15% of propellant is oxidizer, which is 0.5 times mass of propellant, right? And I'm telling 85% is fuel, so 0.85 times mass of propellant. Now what happens? Mass of propellant cancels.
Okay, sir, got it.
So uh, this now you can simply do this n of hmx, and you can end up getting uh, the moles of HTPB also. This is also a way, but if you want to think a more logical way, you can also do in this way. You can take a 1 gram of 1 kg of propellant, and you can see how much division we have in terms of moles, and that is going to be applicable for any mass of propellant. Anyway, so we found out the, now let's try to balance it. That is important, right? So we need to C4H8 N4NO24 plus 0.019 times C200 H302 O2. Okay, now we need to what did I say? I need to first oxidize all the H2O. Okay, so first let's try to find out what should be the coefficient of H2O. So I have how many H atoms? H atoms, I have this side 8 H atoms plus 0.019 times 302 H atoms. Is this clear?
So 13.738.
Okay. So around 13.73 H atoms, which means how many O atom I needed for this?
Sir, half of it.
So how much is that? 13.73 divided by 2.
So 6.86.
6.865 O atoms I need. Do I have 6.865 O atoms? So let's calculate how many O atoms we have. We have 8 plus times 0.019. How much is it? Around 8.038, right? How much I need 650 atoms for H2O, right?
Yes, sir.
So now I have 8. So what I will do is I will subtract 6.865 O atoms, which is used for H2O, used for H2O. Now how many atoms of H2O I form? I'll be forming only 6.865 atoms of mole. I mean moles of H2, right? Which will gives you 13.73 H atom and 6.865 O atoms, right? So once you oxidize it, H2O, how much is remaining? 1.173 O atoms are remaining. Now what I will do, I will go ahead and make oxidize the CO. Okay. So how many I have? Let's calculate number of C atoms. I have 4 in the HMX, right? And then some 200 times 0.019 in the uh, HTB. How much is this? 0.019. I believe it is 7.8 carbon atoms I have. And I have 1.173 oxygen atoms remaining because we first oxidize all the H2O.
So it's 15.2, I guess.
Yeah, 15.2. Is it? So 200 into 019, which is 3.8, right? Plus 4, right? I'm getting. Are you getting 7.8, Anirudh?
Yes, yes,
Okay.
uh, sorry.
Okay, okay, no problem. So we have 7.8 carbon atom, we have 1.173 O atoms remaining. Can we fully oxidize to CO? Will we be able to oxidize it?
No, sir.
Then what do we do? We will oxidize how much ever we can. This is the maximum we can oxidize, right? We can oxidize only how many oxygens we have. We have 1.173 oxygen. So I will take 1.173 from this carbon atom. I will oxidize only this much. And then I will have it as a carbon monoxide. Then what happens? The remaining will remain as a carbon itself. Okay. So in the this 7.8 carbon atoms, I'm going to subtract 1.173 atoms to form CO. Okay. So the remaining would be, how much would be remaining?
So 6.627.
Yeah, wonderful. So we have 6.627 carbon atoms remaining. Okay. And so this is going to be 6.627. You need to note that we are eliminating the oxidation of N, or uh, like N is like, you can say it's a inert species. It doesn't oxidize. It doesn't react to in the product species and come up with NO or N. Okay. In reality, it does. That's where NOx emissions, all the emission rules are there, because NO will be produced. But for our analysis, we'll just ignore uh, the oxidation of N. So what will be the moles of N remaining? So because we have N here, right? So you need to, we have N here, so there should be N on the product side also, right? So how many moles would be remaining? So we have 4N here and then another 4N here, total 8. Is this clear?
So can we make N2 from this?
Okay, yeah, ideally you should make N2. Sorry about that.
Yes, sir.
So how many moles of N2 you have?
4, sir.
Yeah. Because N cannot exist as N. It won't be. N2 is the molecule which exists, right? Yeah. So this is how you find the product moles. How much number of moles are there? Okay, and the mixture ratio, you already found the mixture ratio. It's going to be 0.15 times 0.85. Okay, that is also done. Let's go back. Mixture ratio is done. Moles of product species is also done. The stoichiometric mixture ratio is remaining. We'll come to that later. Uh, if time permits, we will discuss about it. So, of HMX that we need to find out. What is the heat release per mole of HMX? Or the you can say heat of combustion. It's called heat of combustion. What is the heat release per mole of HMX? What is the formula for that? Going to be summation of I reactants HF of Ni. Okay, this is very bad. Summation over reactants N of reactants, where I is reactant, and H naught F of reactants minus summation of Ni products. You remember this formula? It's just formation enthalpy. So the difference in formation enthalpy upon forming this at a constant temperature or at a standard temperature of 298 Kelvin. And that is the reason all these CPs will disappear, because you no need to raise the temperature from 298 to some other Kelvin. Okay? So when you calculate the heat of combustion for any reaction, you need to calculate it upon conversion of this, how much heat is released at the constant temperature. Okay. So if that is the case, and in fact this is for constant pressure process because we are equating enthalpy, right? Um, so constant temperature and pressure. In this case, it's 298 and 180. So the definition of enthalpy of combustion, or the heat of combustion, or the energy released per kg of propellant or per kg of fuel is always at the standard conditions at 298 and 180 pressure, and that is why we have one formation enthalpies here. Okay, so let's go ahead and calculate. This is going to be n HMX H naught HMX n HTPB, sorry, HTPB H naught of HTPB. Okay, and then there's going to be negative, then n what and all we consider? We consider H2O, H naught F of H2O, then NCO, H naught F of CO, and then NC, H naught F of C, plus N2, H naught F of N2. And what we know elements at a naturally occurring state is going to be 0, right, for formation enthalpies. So this is going to be 0 and this is also going to be 0. Carbon also appears as carbon in naturally occurring state, and yeah, N nitrogen is going to appear as nitrogen in naturally occurring state. So H naughts are 0. These H naughts, I think it's already given in the question. So HTPB is given as 78 plus 78, and sorry, HMX is given as plus 78, and binder is given as minus 64. And similarly, CO is what we need, and H2O is given. Okay, let's write it down. Then you can calculate it. It's going to be HMX. How many HMX we have? We have one HMX and 0.09. So HMX is plus 74 plus 0.019 times HTPB, which is minus 64, times minus of moles of H2O. How many moles of H2O we have? 0.6.865 times moles H of H2O, which is minus 268, I guess, or 286, and CO is 112, minus 286, then minus 112. How many CO we have? 1.173. Okay, can you guys quickly calculate delta HC? Then next is temperature, which is delta HC you're getting. Calculate.
So calculate.
Okay. Maybe in the interest of time, I would give you the answer here. I am getting around 2167.5. Please cross check it into kilojoules, because all these are in kilojoules. Please note that whatever we wrote, 74 is a kilojoule, 64 is a kilojoule. So how do you write temperature? Delta HC is nothing but summation of I of products this reactants minus product. This is going to be products minus reactants. Ni of CPI T minus 298 plus summation of minus summation of I of reactants. Remember, this is going to be product minus reactants, and enthalpy of combustion is reactants minus products. Okay, Pi of, so the initial temperature T initial minus 298. Okay, here we will consider initial temperature to be 298 only, so this part is going to be 0, so this whole part would be 0. Okay, so this equation simply simplifies to delta HC, which we already know, 2167.5 into 10 power 3. It's nothing but N of H2O times Cp of H2O times T minus 298 plus N of CO, Cp of CO times T minus 298 plus N of C, Cp of C, T minus 298 plus N of what is the remaining? N2, Cp of N2,
So why is it 0?
which is 0, the reactants.
Yes, sir.
So here the initial
It's
T
already
initial,
at 98
uh-huh.
because it is already at 98, 298.
Yeah, so T initial we are assuming it to be 298 Kelvin. It is, I think I didn't give it in the question, but the initial temperature is actually 298 Kelvin. Initial temperature of are in 298 Kelvin. All the propellant is
Okay,
in
sir.
298 Kelvin. That is the reason this is 0. If not, you need to consider that. Okay. So you know all these things. You know N, you know Cp, you know all the N's and Cp's, which is also given in the question. You just need to find temperature here. So again, in the interest of time, I am giving you the temperature. Please cross check it. Okay, I didn't solve for temperature. Then it's good. You can solve and let me know what is the temperature. And remaining is characteristic velocity. So once you find temperature, what else we need to do to find characteristic velocity? We already covered in the last lecture, last session, right? Characteristic velocity requires, it's actually a function of molecular weight, temperature, and then gamma, right? All these three you need to calculate. So for that you need to know the molecular weight. How do you find the molecular weight of mixture? N of H2O, molecular weight of H2O plus N of CO, molecular weight of CO plus N of C, molecular weight of C, N of N2, molecular weight of N2, divided by N of H2O, N of CO, N of C, and N of N2. This is how you calculate molecular weight. Similarly, you need to calculate Cp of mixture, okay, and then you know R. What is R? R is nothing but R naught by molecular weight of mixture, okay. Once you find, then you can find Cv of mixture, which is nothing but Cp of mixture minus R in gamma. Gamma is nothing but Cp of mixture by Cv of mixture. Once you find all this, you can put it in the C star, which is going to be a function of all these. So I believe that there's going to be a big capital gamma times I think it's RTC, or RUTC by molecular weight power gamma plus 1 by 2 times gamma minus 1, I believe. I'm not sure. Please recheck this equation again. Okay. Okay, there's no gammas here. It's
Sir,
just
it
1
is
by 2.
root RTC upon capital gamma. So it is root RTC upon capital gamma.
Okay, so it's okay. It's 1 by 2 I wrote, but yeah, both are same. And this capital gamma is going to be square root of gamma 2 by gamma plus 1 power gamma plus 1 by 2 times gamma minus 1. Okay.
Sure, the capital gamma is in division with the root RTC.
Is it? Okay.
Yes, sir.
Now is it fine?
Yes, sir.
Just need to find all these things. So only first important thing, if you make a mistake, is if you make mistake in calculating the number of moles, then other all other calculations will get affected. So you need to be very careful in doing this calculation. It's just balance how much O you are going to put here, how much O you are going to put here. It's like filling the bottles. Like first I will fill the smaller bottle, and then I will fill the bigger bottles, like that. Initially you fill everything with H2O, fill everything CO. If remaining is there, you put it in CO2s. If nothing is remaining, then you keep it as O2. If I don't have enough O to oxidize CO, keep it as C, right? If I cannot even oxidize H2, H also appears as a H2 on the other side. So that is how you need to, that is how your thought process should be. Once you do that, all these things are trivial. You just need to calculate all these things. Okay, is that clear? So maybe I will take 2 more minutes to find the, how do you find stoichiometry? Stoichiometry, I think the spelling is right. Anyway, so if you want to find the stoichiometry, what does stoichiometry means? You need to consider ideal set of products. Okay, so here we have C4 H8 N4 NO24, right, plus some lambda of C. This is lambda stoichiometric. Let's call it lambda star C200 H302 O2. Okay, it should give you ideal set of products in a combustion reaction. What is ideal set of products? It should give you CO2, it should give you H2O, and it should give you N2. There shouldn't be any other the what do you say, any other dissociation of the products or any other things. The ideal set is CO2, H2O, and N2. Okay, it's not even CO. So now if you just balance the carbon atoms, let's say if you want to balance carbon atoms, okay, so it's going to be 4 is equal to 4 plus lambda star 200 is equal to, let's call it A, B, and C. Okay, now we have A. Now similarly you do H atom. I think which is easy. I think N is easy. Let's just simply do it. What is N? N we have 8 here, so we will have 4 N2. So that is the problem is solved. So we'll do balance for only other 3. So for H atom we will have 8 plus 302 times lambda star is equal to 2 times B. Okay, and then now we have O atoms. O atoms we have 8 plus 2 times lambda star is equal to 2 times A plus B. Okay, now you have how many equation? 3 equation. And what are the unknowns we have? So it's just algebraic equation, and the unknowns are A, B, and then lambda star. So you can easily solve these two and get what is lambda star. Once you get the lambda star, you can find the mixture ratio, stoichiometry. Okay, so this is how you find. I just thought I will give you some interesting about stoichiometry. So once you find stoichiometric and mixture ratio, you can compare with the present mixture ratio. Let's write it out. What is the present mixture ratio?
So could you explain again about the stoichiometric?
Yeah. So in stoichiometric, what happens in stoichiometry? We have ideal set of products, right? That is that clear? In stoichiometric, we will have ideal set of products. We will not.
Yes,
We
sir.
won't have any dissociations. Like CO2 cannot dissociate into CO and O2. Let's say, or H2O cannot dissociate into OH and H. Okay, that you should remember. And ideal set of products are CO2, H2O, and N2. Okay, so let's say if you have a perchlorate, ammonium perchlorate, the ideal set will be HCl. HCl also in addition it will come. Okay, CO2, H2O, and HCl because chlorine is there. So ideal set becomes HCl. Okay, now what you have to do is you just need to balance these. You don't need to do anything else. You don't need to oxidize CO2 first. You don't need to oxidize H2O first. All these things you don't need to do because you don't know what is lambda star, so you cannot do that also. You are thinking that if I want to form this ideal set of products, how much oxidizer I need. That is going to give a lambda star given by lambda star. So what you do, you form 3 atom balance equations. Okay, so you have 3 atom balance equation and you form 3 equations, 3 equations, and you have A, B, and lambda star, 3 unknowns. This you can easily solve, right?
Yes, sir.
So it's a algebraic equation like x plus y plus z equal to something, x plus 2y minus z is equal to something like that. So uh, you just need to so let's say if you want to do this, yeah, you just need to solve these three equations, and you need to get all these three. Okay, and this lambda star will definitely not be equal to 0.019. Okay, and it will be some other value. Based on that, if you calculate the mixture ratio of stoichiometry, you will get some other mixture ratio. And if you compare this mixture ratio, stoichiometric mixture ratio, and compare it with the mixture ratio what we initially started. What is the mixture ratio we initially started? Mixture ratio actual, let's say in this problem, is going to be 0.15 by 0.85, right? How much is it coming out to be?
So 0.01.
0. How much is it? 0.176 I'm getting. So this is the mixture ratio, that is lambda star, the number of moles of HTPB, right? That is different. Please understand the difference. This is mixture ratio, which is mass of oxidizer by fuel. Whatever you are telling was HTPB's number of moles. Okay, but this lambda is going to help us in finding the mixture ratio of stoichiometric. So let's say if you want to find the mixture ratio of stoichiometric, how will you find oxidizer? What is oxidizer number of moles? Lambda star times molecular weight of HTPB. Then 1 mole of HMX. This will give you stoichiometric, and it might be something. Okay, and this is 0.76, and then you can compare and say whether it is fuel rich or fuel lean. Okay, if it should be fuel rich, then MR of actual should be less than MR of stoichiometry. Okay, it's just for you to compare that how uh, the stoichiometric mixture ratio will help you in telling whether the mixture is fuel rich or fuel lean. Okay, that is the reason I added that question also in this problem. Basic underlying principle is you need to understand how stoichiometric uh, mixture ratio is calculated. Okay, is it clear, Anirudh?
Yes, sir.
Did I confuse?
No, sir, it's clear.
Okay. So just by doing atom balance, you are going to end up in the mixture ratio of stoichiometric. You don't need to do other approximations. Okay, but for a given mass ratio, you need to know how it reacts, and based on this reaction, you need to find the number of moles of each and every species, and based on that, you can find the number of. Based on that, you can find heat of combustion, temperature, everything you can find. Okay. So, if there are any question, you can stay back and ask. By this, I will finish this session. Okay. Thank you very much.